We continue analyzing our experiment using rank-dependent utility. Now we turn to the gammas, the certainty equivalence. Here's the, we measured the gamma 2 before we measured gamma 1 or gamma 3. This was the first figure. From this indifference, we got to gamma 2. In general, using rank-dependent utility to analyze our data is more interesting than expected utility, what we did before, because rank-dependent utility is about realistic empirical theory. So we expect more interesting insights to come from it. Anyway, that's what we're going to continue now. I'm going to present an exercise to you. It's written here. We're going to assume the scaling of utility as we often did, utility alpha j equal to j over 4. And we saw already this is okay under rank-dependent utility. Well, expected utility predicted to gamma 2 equal to alpha 2, but the prevailing empirical finding is gamma 2 smaller than alpha 2. So my question to you is, can you use rank-dependent utility to accommodate that finding? And then it will be nice if you immediately can also, for gamma 1 smaller than alpha 1 and gamma 3 smaller than alpha 3, can accommodate those findings using rank-dependent utility. You can now pause the video, work on it, and after that come back. Okay, I assume you came back and that you did what you want to do, or at least what you are able to do. Now I show you a solution. And we're going to use rank-dependent utility. So we're going to say in this indifference, the rank-dependent utility of that lottery must be equal to the rank-dependent utility of that lottery. That's what the indifference implies under that theory. So I write those two. The rank-dependent utility of the left lottery equal to the rank-dependent utility of the right lottery. Remember, alpha 4 is the biggest outcome. So that probability is transformed. And the rest of decision weight goes to the worst outcome. So indeed, rank-dependent utility gives this equality. Now you see here, this is a convex combination of a big number and a small number. And then the smaller weight we assign to the big number, the smaller the convex combination becomes. So let me write this. But then the smaller this convex combination becomes, the smaller gamma 2 becomes. So indeed, the sentence written here is correct. Well then, we have already seen under expected utility when W half is equal to half, then gamma 2 is equal to gamma 2 alpha 2. Then the gamma 2 in utility terms is the midpoint of alpha 4 and alpha 0. That's what W half is half gives. So then we can simply take W half smaller than half, and then we already can conclude gamma 2 must be smaller than alpha 2, as we just saw. So that's a very easy way to use rank-dependent utility to accommodate this empirical finding. It's in fact necessary and sufficient for it. So that's what we get here. Now, to be sure, I will rewrite the algebra. In fact, I already said it, the solution, but let me rewrite the algebra to say it one more time. So if we have W half smaller than half, then I start writing the equality, the rank-dependent utility equality that results from the indifference. Now, well, we're gonna replace the convex combination weight W half by half. But then, because half is bigger than that, that's what we assume, right? This convex combination becomes bigger from it. So we get that inequality. And we already know that this is utility of alpha 2. So here utility is strictly increasing. It follows that gamma 2 is smaller than alpha 2. To be sure, so now more or less twice I showed you. And now you've seen how it works. Now, if you still want to work on gamma 1 and gamma 3 and see if you can do that for yourself, then pause the video and after come back. Okay, I assume you came back. So then we go on with gamma 1, and that will be quite similar. One extra step to be done. But so this was the figure that gave us gamma 1, or the 50-50 lottery between gamma 2 and alpha 0. The third equivalent of that was gamma 1. Now I go into the algebra. First of all, I write that indifference means we have this equality of rank-dependent utility. The left and the right lottery rank-dependent utilities are the same. That's how we start. Now, the first thing I do is I replace gamma 2 by alpha 2, as you see. Now, we have already seen, we are assuming W half smaller than half, right? Then we have already seen that gamma 2 is smaller than alpha 2. So indeed, we have that inequality. Well, we know that, well, assuming W half smaller than half, then in this convex combination, if we replace this weight for the best outcome, for the best number here, by a bigger weight, because that's what we assume, the convex combination becomes bigger. So we have that inequality. We already know that is utility of alpha 1. So we're getting here utility of gamma 1 is smaller than utility of alpha 1, utility is strictly increasing, gamma 1 smaller than alpha 1, and gamma 3 is a very similar reasoning. I immediately show it. There was the indifference, the figure that gave gamma 3. We get that equality of rank-dependent utilities. Again, we replace gamma 2 by alpha 2. That only makes the thing bigger because alpha 2 is bigger than gamma 2. Then we replace the weight W half by half, and that again makes the whole thing bigger because half is bigger. We assign a bigger weight in the convex combination to the biggest number. We already know that this number written here is the utility of alpha 3. So what we are getting, utility of gamma 3 is smaller than alpha 3, utility is strictly increasing, gamma 3 is smaller than alpha 3. So here we see quite easily and smoothly necessary and sufficient for these empirical findings is W half smaller than half, which is pessimism. It's a common empirical finding. Just if people are a little bit pessimist, then already psychologically you can understand that such a thing can be happening. Now I immediately turn to the deltas, and there we can be short. Rank-dependent utility cannot accommodate what we found by the deltas. We found that the deltas are usually bigger than the alphas, although they must be equal by expected utility, but also by, in fact, just by common sense. Formally speaking, transitivity and monotonicity, stochastic dominance. So very elementary conditions that are satisfied by almost every theory. So this is just a problem where we cannot do very much. Although we can say something, I should say, later we'll be introducing prospect theory that, strictly speaking, cannot accommodate these findings, but it can give some qualitative insights into what is happening. We don't have really quantitative theory to accommodate this finding, but we do understand a bit what is going on. So rank-dependent and prospect theory cannot fully accommodate, but can help a little bit to understand at least. Well, what remains of the experiment is the last questions where you have to give probabilities. That will be analyzed in the next recording, and there a nice surprise will be awaiting us. That is the next recording.